পয়েন্টারটা বুঝে নি। হ্যাঁ, না পয়েন্ট করবো না, এটা এটা আগে এটা পিছে, দ্যাটস অল, পয়েন্ট।
I hope kindly keep your mobile on switched off mode or silent mode. So let us begin today's second day of this mini workshop, and our speaker is Professor Sukumar Das Adhikari. Very, all of you know him. He does not need an introduction here. My very old friend, and one of the person whom I admire a lot as a human being. And so title of his talk is Average of Some Arithmetical Functions and Problems Regarding Visibility of Integer Lattice Points.
So, is it too loud or? So, I will be talking on something which I had worked long back, and in fact, I started my research on these arithmetical functions, average of arithmetical functions, including these coefficients of cusp forms. And arithmetical functions average, because even though arithmetical functions most often their values will be fluctuating, but in average there is some average, they will be nice, and then one tries to find the error term and the bound and fluctuation of the error term. And some of the arithmetical functions, the classical ones, they have some geometric interpretations. For instance, this Rn, this and this Dn. So they count the number of lattice points in certain regions. So they become, so they are a very challenging and popular question. But today, of course, arithmetical functions is not the main topics. So I will touch on couple of arithmetical functions which will be used or referred to, and the main problem is some visibility questions. This was sort of my last connection with analytic number theory. After that, I moved far away from analytic number theory. So, the first I do average of Euler-Stossel, then definition and visibility, definition of visibility and some introductory remarks, then distribution of visible points in the plane and then in higher dimensions, then pattern of visible and non-visible points, then a particular question. So here we take up a particular question which I came back several times. So then first in R2, then in higher dimension, then again in R2. So writing this phi n, sigma phi n Euler-Stossel, it has this main term is 3 by pi square into r square if you sum it up to r phi n, and then there is this error term, and this error term O results meaning this mod of so that means that r of r, this mod is less than equal to some constant into r log r. So this is O, okay, and then of course you know this because exponential is faster than any power of x, so log is slower than any power of x. So this is the Wolf is bound, and there is a history that Saltykov in 1960 he claimed that this power of log r 4 by 3, he claimed 1 plus epsilon for Avit epsilon. But people guessed some problem there, so nobody was referring to that. But Peterman went back to that and found the mistake point and corrected it. After correcting, we get the same Wolf is bound by that method. Then Chawla and Pillai, they had this sigma Rn, you sum at integral points their term, and that is, and then Chawla this result. So this is most often very near x only, this error term. Now omega result is often it fluctuates, because infinitely often lim sup will be. So there is a Chawla and Pillai result 1930, and which says that k is about log x naught, and r of x naught plus 2k minus r x naught is greater than some constant into x naught log x naught, and plus something order of x naught. So this implies, okay, that this Rx is omega x log x. Okay. So it fluctuates, but we don't know in which way it fluctuates. Omega means in some way mod of Rx either goes up constant into x log x, or minus some constant into, we don't know in which direction. Regarding the sign change, Sylvester in 1883 conjectured that for integral values Rx is always non-negative, but he missed. In fact, he himself made a chart where he missed an 820, I think. Yes, 820, the value is negative, that Sharma found it, and Sylvester had missed it. But then the question whether Rn changes sign infinitely often remained unanswered. Then in Erdos and Shapiro 1951, their averaging technique, they found that both sides it goes, because that only omega there were less log, and here you see 4 logs, but it says both ways it goes that this much. Then Montgomery modified same Erdos Shapiro method with some more tricks, and he improved it to omega plus minus x root log x. And this we also tried to simplify Montgomery's thing when we were doing something, and we remove some analytic part by some elementary arguments. So, but anyway, it is Montgomery's only. Then there is a conjecture that this is O of x log x and omega plus minus both sides x. But as far as I know, nothing more happened. People tried something, they did around that, but this much only. Somebody else, there is a 2017 paper where also they just recover Montgomery's result only. So now after with this we start, there will be another arithmetical function coming in, we will talk when it comes, but we start with defining lattice point visibility. So lattice points, you know, because we are mostly considering these integer lattice points. Suppose this is 1 1 and this is 2 2. So, and this is will be somewhere 3 3. So when you join, this is in between 1 1 and 2 2. So this is as if blocking the view from this. So the 1 1 is not visible from 3 3. Okay, and 1 1 itself considered to be visible from itself. So the definition is, if there are two integer lattice points in d dimension, with the we are always talking about rectangular Cartesian coordinates, then the points alpha and beta are visible from each other if either it is there is same point, or the line, what I explained, line segment doesn't have any other point in between. Now you see that if GCD of these things is some t, then writing I is equal to TAI dash, you see that on the line segment there is a point, this A1 dash, AD dash which is sitting in between and blocking. So, and same thing other way also. So that means we get this visible from origin if and only if GCD of AI is 1, okay, if and only. Now, since 2 points these, they are visible from each other, is same as if you drag them, so it is easy to see that A1 minus B1 etc. AD minus BD, that point is visible from the origin. So therefore, from the earlier observation, if their differences are GCD is 1, then the points these alpha and beta are visible from each other. Now, for a real number R, this n dash R be the number of integer lattice points in the square. Okay. So, mod x less than equal to R, mod y less than equal to R, which are visible from the origin. So, let me come to the picture. So, here that we take one of the 1/8 part of that and look at the lattice points by symmetry, and you see that points on the line starting n0 to nn, the lattice, forget that line, and then n1, n2, nn. So, these are the points which are visible from the origin, and then you have to multiply by symmetry by 8 into that, and that origin itself is visible from itself. So, that gives that 1. So, you see that this question boils down to this sigma phi n, this number of. Now, so write like this, then we know that even Martin's one was order R log R. So, once you put it here, then n dash R by nr, okay, this number of lattice points by visible lattice points. So, that tends to 6 by pi square as R tends to. So, that is 1 by zeta 2. So, we will see in the higher dimension also. So, this is, one can say that express this phenomena that this density of integer lattice points visible from the origin is 6 by pi square. Now, for higher dimension, the similar thing happens and you get this, okay, and here the function which comes in place of phi function is this Jordan-Townsend function, okay, which is the number of k tuples of positive integers all less than or equal to n that form a co-prime k plus 1 tuple together with n. So, similar thing, but here this that I worked with Shankar Nayan, and we have exact the order of the fluctuation of Jkn is very nice and well understood. So, here the visibility question also much better understood. So, now there is a pattern. So, pattern is like this. So, if you have a grid, you put some places 0 and some places cross, some places 0, some places cross, and some other places you may not put anything. So, what we want that this pattern is visible, is realizable if we can put it on the plane somewhere such that from origin wherever this comes is visible and this comes not visible. So, if you, so let me see. So, a pattern is PD is realizable. There exists a cube after shifting. Okay. So, this is visible point whenever this is a circle, and what I told, and non-visible when it has a cross. Now, Harjak and Stewart, they gave a criteria when a pattern is visible. In fact, they gave the criteria if these circles, if you take the circles, mod any prime, they should not have a complete square. So, in particular, you cannot have 4 this visible point like this, that is not realizable. So, this is the general some remarks on visibility. Then we go to a particular question, and our talk will be mostly on this only. So delta ND is in d dimension, and where each coordinate is from 1 to n. So we have from this is 1 1 and this is n. So this is the square, and A and B, now two subsets are visible from each other if any point of B is visible from at least one point of A, then we say B is visible from A. So suppose we put some guards in few places, when every place of the garden is visible by some guard, then we say that this well guarded sort of. So now define FDN is minimum of the size of S such that this cube is all lattice points in the cube is visible from those points, and minimum size you want, that is you have to put guards, then you try to put less number of guards. So the problem is to find the exact order of FDN. Okay, and this was in many times it appeared. There is a Mozart list of problems. Then it is Brass, William Mozart and Janos Pak research problems in discrete geometry. Then it is also Richard Guy's problem books, and then there is a Lison and Sick. There is these explorations on the visibility of lattice points. So these last two authors, they try to give many. I don't know whether this is, to me this question is anyway interesting, but he tries to make as if there is a school band, and then there are some students have cameras with them, and they try to take photographs so that the union of this thing they don't miss any student. Okay, so that everything is visible. So minimum number of cameras. So like that. But I can give some buildings. You put guards on the buildings. So buildings are kept at this like in a grid type thing. But these are just a way of, if you understand mathematically, that is enough. So Abbott was the first who worked on this thing in 1974. He gave upper bound and lower bound. So the lower bound by Chinese Ribbentrop theorem, they found that if you take this many points, there will be one point which will not be visible from those points. So you need more than that. And up one they get by greedy algorithm. So you take maybe the origin, then whatever the points are not covered, you know that 6 by pi square into that are covered. Whatever not covered, then most of them are covered by what? Then take that point, one of them. Then each time you do, then because of that bound, I will not go to that technical thing, that follows, upper bound follows like that. Then this is the argument. Then Erdos, Gubar and Hammer have a book. So they have a lot of, that is book is called lattice points. So there are many various problems on lattice points. So they remark Abbott's proof is an existence proof and gives no indication how to construct small subsets from which any point of the set is visible. It would be of interest to construct such subsets of cardinality at least satisfying the upper bound, if not 4 log n, say some k into log n. But actually they had a result. About this result it is said, but they had a result. I will take the whole thing. So there is Jakob-Stahl function. This Jakob-Stahl function is defined by, it is the least integer such that when you take a plus 1, a plus 2, from any a, you take consecutive gn integers, then at least one is relatively prime to n. So trivially it has to be, if you take n plus 1, 1 will be 1 mod n. So there is, so it is less than equal to n plus 1 anyway. But of course I will come to that. So then what is this? how does that work? That it's so on this line, we now we don't take Gn because Gn fluctuates. In prime, it will fall down. So you take some Tn, which is an increasing function, but which bounds Gn. Increasing, but it is more than Gn. So then we take that Tn on from that line, consecutive lattice points 1 1, 1 2, 1 3, 1 Tn. And then we take one more point 2 1. So what is the idea? Take any lattice point xy. Now xy is visible now when you or not from 1 1, you see that difference is x minus 1 has to be relatively co-prime to that y minus 1. But as you go on moving y minus 1, y minus 2, y minus 3, the consecutivity is changing. So one of them has to be because of Tn, as it is defined, it is upper bound of Gn. So there will be one of them will be co-prime to that, to x minus 1, and so that is it will be visible. So this is the argument. So you got how many points? You got Tn and one more point. Because why this 2 1? Because after 1 Tn, if you take 1 Tn plus, after that all those points will not be visible by any of these points. So from 2 1, all the points of the line with first coordinate 1 will be visible. So this is the argument. But then we have to come to Gn. Gn, as I told, that trivially it is less than equal to n plus 1. But Erdos proved that it is upper bound is O of log n to the power alpha for some finite alpha. Okay, and even it Stevens, many people worked, and one has this where little omega n is the number of prime factors, distinct prime factors. So it is expected value is log n to the power 1 plus epsilon. So the thing is that even now beyond that, okay, beyond 2 itself is very difficult, okay, because that will be giving Linux result on the least prime in arithmetic progression, which is very difficult. So this going beyond 2, improving beyond 2 is very difficult. So that problem is like this, difficult. But even if it is we solve, suppose 1 plus epsilon expected 1, that will not solve our question, because still we will get something which is not of order log n. Okay. So then that's what I remarked here. But then in 96 with Balasubramanian, so we proved that one can give an explicit description of a set from where this whole grid is visible in the plane, where xn satisfies bit better, because you see the upper it was this 4 log n. Okay. So we didn't go this log n by log n, but there was one log n factor. That's what we are poor in that, but we are much better than log n. So not only we our thing came in answer to Erdos question, okay, but what we could do slightly better. But then let us see what is the method. So this upper bound of Abbott. Now what is this basic idea? First up we translate that this x coordinate by small amount. Then one hits an integer, sum of reciprocals of whose prime divisors is strictly less than 1, and that implies that g of x minus a is small. So bit more explanation. Okay. So let us take S, okay, it is knowing Professor Balu, he will put some arbitrary, which okay, that is his thing. So it may be you need 50, but he will put 1000 log n by log n, and there is 1000 something, so that there is no doubt that it would work. So then there exists a t such that if you take this, okay, that t is about constant times log n, and you by slight shift you can bring it, and this you average and break in 3 parts. So analytic number theory is like Stephen will see. So there are 3 places we break: log, and then log square, and beyond that. So in first one, because of sigma 1 by p square, that will give you some, that 7 by 10 around constant. So that gives that it is less than 1. Less than 1 is enough for us. So we will not go to prove that. Now they consider the integers in an interval of length s. For any p dividing x minus a, there can be at most s by p plus 1 multiples of p. Therefore, the total number of integers not co-prime less than equal to this, and then since sigma 1 by p is less than 9 by 10, you get this, and the upper bound of omega is 2 log n by log n, so you get s minus 1. So that once it is this, then you are through. So there is, so that means g of this is less than, so 1 is co-prime, so you got it within that. So you translate x coordinate little bit, and you bring your g value less than log n by log n constant time. Then what we do? Again same thing. Now instead of a line, we take a rectangle of height s and breadth t, and then you shift your x, it is x minus a by a y, and then that you try, okay. So by that what you prove that your this has g has gone down now, so you will get in that. So by the same argument as we did earlier, because we are using both the these things which they didn't use, because we have both the coordinates, we can shift little bit. So now some results on omega n, because we wanted to do it a bit better. Even though we solved Derrida's question, our upper bound was more than the lower bound. So still it was in my mind. So I was thinking, then but I'll come, we need something on. So omega n is already I mentioned, and upper bound, as I told, 2 log n by log n. Now a quantitative version of Turan, of the Hardy-Ramanujan, this normal order of omega n, those who know. So this is the precise thing. Number of n less than equal to capital N, such that this is greater than 2 log n is less than equal to n by log n. So this is with a quantitative version. So what we did with chain, that if we E and H, if we define the number of positive integer less than equal to n, such that your that omega function is greater than equal to that h function. My h is an increasing function, and this happens, then the set a set Zn can be given such that the whole square is visible from Zn, and some exceptions will be there. That exception is 100 times the size of E and H square, okay, and this Zn size is this much, okay. Now let us see corollary. So if you take Hn is equal to 2 log n and use that Hardy-Ramanujan quantitative version, then you will see that at most so 100 n square by log n square exceptional points will be there, and Hn, that size will be log n log 4 times n of that order. So this is that. And then if you go, H is the same, the full bound of 2 log n by log n, that is bound of omega, then there is nothing left. So we see everything, and then you get this ln is equal to 1600. But you see, again we got the same upper bound. We could not improve the thing, but we could have calculated that constant in my paper with Balasubramaniam, but that time we didn't care. But here it was easier. It came 1600. It came. So with an explicit constant, we got the same result again. So that now we went to higher dimension, and higher dimension, the same lower bound works in the same way, and here we could get that where that this upper bound we could get log n by 2 log n. So here we got the exact what we wanted in the higher dimension. Okay. Now later Chen with his student, they looked again and they tried to find the constant, and they did the constant upper bound is zeta value of d minus 1 in d dimension, and the lower bound for they define another function f dn, whereas small f dn is those points from where it is visible, but they are inside the cube. But it can be anywhere, then you call it FDN. Of course, FDN, capital FDN will be less than equal to small FDN. But capital FDN, they get the upper, that lower bound d into log n by. So that is gives the lower bound of small FDN also. So FDN is bounded by 2 zeta values. That much was there, and then with Granville, we attacked this to try to finally solve, and so for every integer d in that means any d dimension, if you take that lattice points in d dimension, the set of lattice points inside a rectangular box with all sides parallel to the axis, and shortest side is capital N. Okay. Then there is visible from some beta, which is zeta d into log n by log n. Okay. So here we will give bit more general what we did, that let us define RDN. One side is length n and other side is free. All these varying over all z elements. So it is like that if you take in 2 dimension 1, 2, 3 up to n, and then y coordinate the whole one. So that one is RDN. Now for any integer d greater than equal to 2, this cube is visible from some s. If some s, then s has to have sides zeta d, and but that s is anywhere. Now wherever it varies, because they are getting different bound, but if s is anywhere, then also lower bound has to be zeta d into log n by log n. And there exists something always inside this offside zeta d into log n by log n, such that RDN is visible. So one side is 1 to n, other side it is 3. So that means a big rectangle, infinite rectangle is visible from this side. So this is our. Now there is a question, one question we posed, and that is that question. For any set of the lattice points in d dimension, let nu s be the size of the smallest set of lattice points from which s is visible. Now what is this VDN, that d is the dimension, we do as a s size is capital N, but s varies over all subsets of lattice points in d dimension with that size. So as we vary s, what is the maximum Vs or nu s, whatever. So we could show that this is like this, upper bound and lower bound. Again, there is a difference now. Okay, top again log n, constant time log n, and here it is as the initial Erdos string was there. So regarding this problem, we came back to that situation. So we posed that question whether it is now one can bridge this thing, and there should be some open question. But as far as I know, I mean, nothing happened so far regarding this question. And regarding that, what the method in with Granville, again we used same lower bound, that some sort of Chinese Ribanda theorem, but with bit more clever way. And upper bound, this also greedy algorithm. I mean, one can say we became more greedy, and by prime we became tried that way. And I don't want to be technical, so that gave this final thing. So with this, maybe I'll stop. That is at dimension 2. In there it is zeta d in dimension d. That is yeah, 1 by zeta d. Uh, uh, hmm, hmm. No, there are many things that are done. We see one can think of many problems. Like somebody thought that the way that it is 6 by pi square thing, what region it does. So if the it is bounded by some region, no, and that is rectifiable curve, then again it is 6 by pi square. It happens. Then there are questions like me and Francesco, we did it, which I didn't want to go in the function space. Function, you take a polynomial ring over finite field, and then again you do that those relatively co-prime, how many, and there this d is the use the degree for the size, and then again same result comes. Then there are some people who have done, instead of visibility line, they change. That is not very old, recently last few years, that they change that there is some curve. So in that curve there should not be some point in between which obstacle. So people are doing many things nowadays, because as I told you that I don't keep track of this much. Only last few days I tried to see what happened. Okay, so and I don't want to go back also to this maybe. So I just told it some reason. Yeah. This is because there is this. I showed somebody this paper of what is that? That many computer science people. Is this paper? I think I left it there, or yeah, like Salit paper, the state complexity and Jacobson function. Okay, then because the way the Jacobson function we are handling, so they quoted our paper and did something, and there was some many other computer science papers also. They do this these things. Okay, all. Yeah. Might have been done, but those some of those things, those non-analytic, we don't keep track that much in computation one. But the Shalit's paper is yeah, state complexity he is calculating. So I roughly saw that they sometimes need this function. That's why. No, T is there. Yeah, just to go out and the left. Yeah, let us go.
Conjecture, and this Boyle is precisely the Boyle whom I love. Huh?
Very and Professor Adhikari for giving me opportunity to speak here. This is Emil Borel's conjecture, not Armand Borel. Okay, this is about digits. Yeah. So we fix integer b greater than or equal to 2 and we write real numbers in b array expansion. So b equal to 10 is what we use, decimal. Okay. So this A's are going to be digits. So this is all A's are in between 0 and b minus 1. We are going to consider only closed open interval 0, 1 just because we are interested in the after decimal what happens. Okay, after decimal only we are interested in. Therefore, the result is true for any real number, but the point is fractional part we will be considering. So we restrict our attention to open interval 0, 1. Okay, so if alpha is rational, we know that it is if and only if the digits are periodic or eventually periodic. So therefore there will be patterns already. Okay, so we are not going to consider right now. So we will look at the irrational side. So if alpha is irrational, then the digits are not periodic, but not all is lost. There are patterns still we can able to look for. Okay, we can still talk about patterns among the digits AIs, and then using the patterns we can infer some information, get some information. So for instance, your cell phone number will be appearing in the digits of almost all real numbers. It's a big statement, right? And that too not, it's just not once. If I choose first m digits, m is very large. How many times it would have appeared? M by 10 power 10 times. Exactly. You keep on increasing your m, this cell phone number will be keep appearing. Every cell phone number, it's not just one. Okay. This is Borel's theorem. I will be telling more technically. B I have taken to be 10 just because 10 digits, 10 digit cell phone number. Yeah. So we will talk abstractly. The same thing, concept, we will write it in abstract form and then we will try. So block of digits B0, B1, Bn minus 1 is a n length block of digits. I call it B in the base B. B is fixed already. I am looking at in that block only. In base B, I am looking at n length block. Then given a alpha, irrational or rational, whatever, given a alpha, first m digits, how many times this block has been appearing? So for instance, for me, so A1, A2, A100, if I take 100 length block. So I have taken 100 length block B, A1, A2, A100, A2, A3, A101. These two are distinct blocks for me. It may happen that this block is 1, 1, 1, 1, 1, 1 always. And if I have string of 1 lakh 1, 1, then I would have had many more distinct blocks of length, this 100 length, 1, 1, 1, 1. Okay. So the counting, this is the way I will be counting. This NB M alpha, which counts the given block B appearing in the first m digits of alpha after decimal. Okay. So maximum it will be m minus n plus 1 only. It is possible. Maximum distinct blocks, not disjoint, distinct blocks. Okay, this NB is the number of times counting function. Then I say that this given block appears in alpha with the frequency nu. It means the limit of this number divided by total what I am considering m length, first m digits, divided by this quotient should converge to a number. This is always less than or equal to 1 and greater than or equal to 0. So it is, this nu is a frequency between 0 and 1. Okay, the given block appears in alpha with the frequency nu, means if I choose large enough m, first m digits, it would have appeared with m nu times, that is proportion of nu. A real number alpha is said to be normal to the given base b if for every length n block should appear in alpha with the frequency 1 by b power n. See, once n is fixed, suppose 100, n equal to 100, how many distinct blocks of length 100 I can have? So first box, suppose 100 boxes are there, each box I am putting 0 to b minus 1, b choices. Therefore, b power n distinct blocks of length n will be there. So 1 by b power n, the given b should appear with the frequency 1 by b power n. This is true for each n. Then we say that each n means block also gets changed. Okay, so then we say that alpha is normal to the base b. Okay, if alpha is a normal number to the base b, then each digit is also appearing with the frequency 1 by b. Every block is also appearing infinitely often, but more than that with correct frequency. Okay. So for example, this is the cooked up example. You look at integers 1, 2, 3, 4, 5, 6, natural number 1, 2, 3, 4, 5, just to put concatenate way. So this is the after decimal. If you put, this is the number you will get. Okay, this number is normal to the base 10. Of course, you can take 2 base, you write each integer in base 2, you put all, that is normal to the base 2. But if I, given this number, if I change my base from 10 to 2, then I don't know this is going to be normal or not. That is not proven yet. But this is normal, people have proven. Okay, it also needs a proof. Looks like all patterns are there because all natural numbers are sitting inside, but still with the right frequency one has to compute. More interestingly, if you just put all primes after decimal, 2, 3, 5, 7, 11, 13, 17, etc. Only primes, you just put the digits. This is normal to the base 10. So, or you take a polynomial with integer positive coefficients, for instance, f of x equal to x square. You put f of 1, f of 2, f of 3, that is normal. So this is Erdos result. One needs a lot of, proof. Okay, just I am telling you. What E. Borel proved in 1909, in the sense of Lebesgue measure, almost all real numbers are normal to the base b for every integer b. So that's why I said your cell phone number will be appearing in almost all real numbers with the 1 by 10 power 10 frequency in base 10 because of this result. Any rational number is not normal just because it is periodic, therefore some pattern has to miss. If you take Cantor set, yesterday talk of Stephen, he mentioned this point. In a Cantor set, any element, one digit is missing, the digit 1 will be missing in base 3. Okay, therefore it cannot be normal because every digit has to appear. First of all, it has to be normal. Okay, and therefore uncountably many non-normal numbers are there, but still set of Lebesgue measure 0 within that. Okay, so though the set of algebraic irrational is countable, it is of Lebesgue measure 0. Borel felt that these numbers should not be in the exceptional set. It should be belong to his theorem type because it is except Lebesgue measure 0 set, he proved that theorem. Therefore, countable set, whether it is sitting inside or not, nobody knows. So one needs a proof. So he conjectured that any algebraic irrational number will be normal to every base b. Till now we don't know single example for single base, even 2 basic base b equal to 2. We have no, I mean there is no result about giving some frequency etc. It's unknown, completely unknown. Yes, square root 2 is the simplest algebraic irrational. We don't know whether it is normal to the base 2. Conjecture. Yes, sir. Example of normal to a base given base b, some base b. We don't. The whatever examples I gave, all are transcendental. That concatenating all the or f of x equal to x square, all are transcendental. One can prove. This algebraic side, we don't know example. You will see what are the known result. From that, it will be visible for you. So 2008, in base 3, one of these two patterns, 0, 1, 0, 0, 2, 1, 2, 0. One of this will be appearing infinitely often in every algebraic irrational. This is coming from automata theory. That's why is very specific thing it is popping up. Otherwise, the first they should prove that okay, one will be, of course, if I take a base 2, if I take all algebraic irrational, 0 and 1 has to appear infinitely often. If 1 is finitely many, then 1 is appearing every time, then it is going to be rational. So only we know base 2, every digit is appearing infinitely often. Base 3 onwards, still we don't know. Every algebraic irrational doesn't miss any. Okay, otherwise it's a counter example to that. Okay, so this is a very short paper, but coming from automaton theory. In 73, Mahler, what he proved is given a alpha irrational and a given block B, he gets an integer x such that x times alpha captures this B infinitely often. After multiplying by integer, the fractional part of x alpha will be having this given base b, and this x also he gives a bound. This x should be, the base is b, n is given, n is the block, given block length. So x is in between 1 to b power 2n plus 1. There exists x such that x times alpha captures this block b infinitely often. Of course, this is true for algebraic irrational also. Generally, it is true for any irrational number. But here, of course, x is, we don't know what x is it is, because you have several choices of x and one cannot pinpoint. Existential. Existential. This is the theorem we are going to see later more. In particular, if we take, okay, that is the same. One more thing, so I said given n, there are b power n distinct blocks of length n. So we put all the blocks of distinct blocks of length n in concatenate way, and we make a one block and apply this theorem. Then we get 1x such that x times alpha captures all the distinct blocks of length n infinitely often. That's one way to realize. This is only for infinitely often. Frequency computation is out of question. The same thing I have said. So just put all the b power n distinct blocks together as a block, one block, and apply Mahler's theorem. You get x such that x times alpha captures all the patterns of length n infinitely often. So there were improvements. So first Mahler he gave the bound for x b power 2n plus 1. After that this was improved a bit, b power n plus 1. In 94 they could improve this, the bound for the integer. Oh, acha. Okay. So in order to prove algebraic irrational alpha is normal, first step to prove every block of length n occurs at least once. Okay, then infinitely often, then computation of frequency, etc. Okay. So in that Euler's theorem, the trouble is that given alpha algebraic irrational, x times alpha only captures. Therefore, you cannot say all algebraic irrational we exhaust or not. So still this is interesting. Once appearing. Oop. Too much. Oh, again it's that particular point, it's something. Okay. Okay. So I count this function, complexity function, this is called P alpha Bn. In base B, alpha is algebraic irrational and n length block, how many, at least once, how many distinct blocks of length n appearing at least once in the fractional part of alpha. That is the complexity function B, P of alpha Bn. That is from one, definitely one block has to come because it is a non-zero algebraic number, algebraic irrational, therefore one block has to come, 1 to b power n maximum. One has to prove it is equal to b power n. Okay, it's the exponent in n. So by the application of subspace theorem, Adamski and Bujow, what they proved is this is this function divided by n that tends to infinity. Means we have to say it is exponent in n. This says okay, a little more than n. That's the reality. That too large enough n. That is, I will come to that. Okay, so since subspace theorem is entering, I just because I need it once more for one more application of this. The above result has been achieved by proving a transcendental criteria. See here, by assuming alpha is algebraic, he wants to count. Okay, suppose this limit is finite. You assume limit is finite, some kappa. Then P of alpha B n is less than kappa n. Okay, for all large n of n's. So using this, see, number of distinct blocks appearing in alpha is very less. It means many things has to be repeated. Okay, that repetition, using the repetitions, he proves that this number has to be either rational or transcendental. That is why they get into transcendental criteria. By alpha, if alpha is rational, then of course periodicity is there. Even if it is not irrational, just looking at repetitions of lengths, I mean the digits, you can able to capture some transcendental criterion. It's weak, but still that gives this. The weakness coming from that only n they could do. If it is stronger enough, it can go more than. So that has a limitation. So that's why they first prove transcendental criterion, and assuming that limit is finite, then use the repetition patterns. They prove alpha must be rational or transcendental, which is a contradiction. They assume that started with algebraic irrational. Okay, so that's the way they prove. I will come to subspace theorem. Before that, I will where we are leading to. Q is dense in R. It means, of course, this statement everybody knows. Given a real number and epsilon, I can get one rational number epsilon close to that real number. But this is not enough to predict what kind of real number you are looking at. So the epsilon is, once epsilon is fixed, then you cannot really predict the real number. If epsilon is floating, then you can able to predict the real number. That is what the idea of Dirichlet. So what he proved, if alpha is irrational if and only if there are infinitely many rational numbers you can approximate with the alpha with 1 by q square. Epsilon is now floating here. So 1 by q square, whatever rational number you are approximating, the denominator, with respect to the denominator, that epsilon is there. Okay. If you can do that, then you can predict that it is irrational. Then this was the first starting point of, okay, different way of looking at how to give transcendental, possibly study transcendental using rational approximation. So then usually once some result is there, then they try to improve, whether one can improve the exponent or not, or some constant you can add or not. So what they found is you can replace q square by a times q square, where a is at most square root 5. Then only then you can achieve this result. Okay, so you can improve. It's in some sense it is tight. If you improve anything, that means you will lose some irrational number. That's what, except some irrational number, you may be able to improve. Okay, this then Rath final. This is the final. This is the first ever criterion for transcendental. Rath proved in the same line of thought. If alpha is algebraic irrational, there Dirichlet, he studied all the irrational numbers. Here he assumed alpha is algebraic irrational. Then this inequality you can have only finitely many. So this way of just improvement, you see, so q square plus 2 plus epsilon. Even this will have finitely many. Okay, suppose if I have a number, suppose many of the series, if you take many of the known series, then the real rational approximation is the partial sums will be rational. So if you can manage to put the partial sum and approximate more than this, then that series must be transcendental by this theorem. Okay, so many of the series type transcendental will come from here. So for instance, this series 1 by 2 power 3 power n, the sum, this is transcendental, just because the partial sums will beat this inequality. That's the reason. So you can produce more. Then Lang came up with okay, q power 2 and q power epsilon is there. Whether we can improve that, still finitely many solution. Q power epsilon, generally if you want to replace, then logarithm of q powers. So what he suggested is logarithm of 1 plus q, means we are enlarging the interval and we are asking for finitely many solutions. Okay, so that is the conjecture of Lang, still unproven, but log 1 plus epsilon is really important. If you take less than this, then we know infinitely many solutions from Kingin, another result of. So this is kind of optimal, but nobody knows how to prove. Okay, so why I came to this, the subspace theorem, analogous version of this Lang's subspace theorem, which is needed to improve Peugeot's result. Okay, so 2014, Anup Dixit, Purushottam and Anand Shankar, they formulated a version of subspace theorem. This I will tell the classical also how it is. This is, we call it subspace Lang conjecture. Given a n, we look at, we fix a finite set of primes, which includes infinite prime, means a usual absolute value, usual or absolute value, distance function. Finite set of primes, we are going to look at the periodic absolute value. Okay, so finite set of primes and infinite prime we fix. For each prime p in that finite set, we create a linear form with algebraic coefficients, L1p, Lnp, n linear forms in n variables. Okay, so then we look at the product. When we plug all, I mean the linear forms, we look at the product and we plug integer lattice points x1, x2, xn. Okay, the product should be very small. You collect only those integer lattice points such that the product of linear forms after plugging, it is very small. Okay, this set lies in only finitely many proper subspace of q power n. Okay. So this is this is the subspace theorem. Here here why it is Lang conjecture comes, usual subspace theorem, the h logarithm of n power n minus 1 plus epsilon, instead of that h of x power epsilon will be there. So that is replaced by logarithm power. That's why it is subspace Lang conjecture. Usual subspace theorem is without the logarithmic factor, just power of epsilon. Okay. So if the product of linear forms values are going to be very small at the integer values, those values will be captured by only finitely many subspaces. This is very, I mean, when we look at it, this is not really applicable to transcendental, but this is the most powerful tool in the theory of transcendence. H is the height. I am not defining here. It's here it is maximum of the coefficients, but you have to take off all the periodic values also. Okay, product of max of 1 comma xip, the absolute value. This is a Weyl height. Infinite prime means usual absolute value, usual normal in R, real line. Otherwise periodic absolute value, because any absolute value over Q is either periodic, equivalent to either periodic absolute value or usual absolute value. That's Ostrowski's theorem. That's all we need. This has a number field version that is much more useful than this particular. Just I have written it for only Q. If one assume this kind of statement, then whatever Bujoe proved, what Bujoe proved is that this function p alpha bn divided by n tends to infinity. One can improve this by assuming that subspace Lang conjecture. So this can be proved that this function is more than c power n. That c is also not touching the what exact value we want, p power n. C can be taken to be b power 1 by 16, kind of. Still, even by assuming the subspace Lang conjecture, we are not reaching what is the real. This is for only once appearing. So not even infinitely many, not even frequency computation. Okay, so I am going to present my paper on, we did it in 2018. This is on Malus theorem. Let me recall. So given a irrational number in 0, 1 and a given block B, I can find an integer x such that x times alpha captures the block B infinitely often. Okay. So the trouble to compute the frequency is that this x given a B, I will get one x. Yeah. If I change my B, of course I will get different x. I can keep changing x. Okay. The computation of frequency of B occurring in base B of the expansion of the above theorem, that is our aim. We want to compute a frequency, but of course with this current knowledge it's impossible. So under some assumption, it should not be like unknown theorem kind of conjecture. No. Okay. Suppose if it is Borel conjecture is true, at least some pattern has to exist with the correct frequency, right? So if you know one pattern correct frequency, whether we can get other patterns, that's that kind of theorem we are trying. This is the combinatorial lemma which is crucial. Okay, alpha is irrational number written in base B. Suppose I know that 0 block is appearing. 0 block is appearing in alpha. Whether I can push, the theorem says there exists x such that you can push the given block also. Theorem anyway says, the Malus theorem says alpha and a block B, you can always get X such that X times alpha captures the block B infinitely often. Here we are asking, suppose I know 0 block is appearing in some position, whether I can push this B in the same position after multiplying by X. Okay, then only then I can, if I assume, suppose 100th position, my last, the 0 is appearing, and 95 to 100, so for 5 length. When I multiply by integer x, x alpha, whether in the 95th position to 100th position, my block B is also appearing or not. If I can prove that appearing, then if I assume the frequency in 0 level, then the same frequency will happen in x times alpha also. Okay, that's the idea. So in fact, we can only with one twist, we need to know not only 0 is appearing, but the next non-zero digit we should know. If we know, then we can able to push in the same level, same position, the given block. So it says 0 is appearing in h0, h0 plus 1, etc., h0 plus n minus 1 position. Okay, and h0 plus n, nth position is non-zero. That I have to know. I cannot push it in between next also 0, then I cannot do that. I need to know this is non-zero. Then the given block can be pushed after multiplying by x to alpha, that same place it will be appearing, B0, B1, B2, etc. But the digits may be, I mean the general, after multiplying by x, of course many digits will change, but h0 digit is going to be B0, h0 plus 1 digit is B1, etc. Same position it maintains. Okay, this is for one particular. Suppose if I know one information, then I am pushing in the same place after multiplying by x. This is just combinatorial. Okay, I just assume that a h0, a h1, etc. all are 0, and a h0 plus n, n plus 1th level, it is non-zero. I will assume that h0 plus n is h1. H1 is h1th place, it is non-zero. So alpha I can write it as a series ah by b power h, summation ah by b power h. So I will separate this series into two parts. One is rational partial. Okay, next. Okay, so if all are 0, then already we have. So we assume that one of the BAs is non-zero. So what I am taking first, I know that up to h0 plus n minus 1, h0 to h0 plus n minus 1 zeros are there. Rest all we don't know what is in before first place to h0 minus 1. So we take the partial sum up to h0 minus 1 just before 0. Anyway, if I put next digit also, it is 0 only. It is not going to take. Just partial sum. Just before 0, I am cutting it. Then I should have taken the next tail, but I don't take the next tail. What I do, b power h minus 1 times, I multiply alpha with b power h1 minus 1 times. It means what? Suppose in the decimal expansion, 10 power 100, if I multiply, 100 digits will be just shifted. That's what I'm doing. So that is, the tail would have started with a h1 by b power h1, but here it will start with a h1 by b, then a h1 plus 1 by b square, etc. Since alpha is irrational, t is irrational, because s is rational, finite sum, the t is irrational. So and first place is a h1 by b. A h1 is non-zero, therefore this is at least 1 by b, because non-zero digit at least is 1. Okay, so this lower bound is important. So therefore I have a tail t. It's not really tail of alpha, something twisted. This irrational number in between 1 by b to 1. So I rewrite my alpha as x s plus, since I multiplied multiply by b power h minus 1. If I divide, then I will get my tail. Okay. So that's what I have written, s plus t by b power h1 minus 1. This is my alpha. Alpha I rewrite in different way. B is the block, b0, b1, bn minus 1. I rewrite in terms of integers. Usual way, B array expansion of integer. b0 times b power n minus 1 plus etc. bn minus 1. This number, this is a block, but I am treating it as an integer now. This integer is at most b power n minus 1, because maximum is b minus 1. If you put, you will get the upper bound b power n minus 1. At least 1, because it's a non-zero block. So our this t we are going to use. We want, so we have pushed this. We are looking at t where in the h1th place. It's starting with h1th place. So somehow I want this. When I multiply by integer alpha, so it means I multiply x by t also. Okay. This x times t should be an integral part of something. Okay, this b, the integral part of x times t should be my b. Means then only then I can able to capture this b0, b1, etc. bn. Okay, the integral part of x times t, when I multiply by x times t, the integral part should be like b. Okay, that's why I am doing this work. Okay, for any natural number k, the length, since t is less than 1, k plus 1 times t minus kt is less than 1. So therefore, if I take interval b and b plus 1, there exists an integer x such that x times t will be fall in this. Once x times t is an irrational number, fall in this, then the integral part is going to be b only. Okay, that's the idea. Okay, that's why I multiply by b power h minus 1. You will soon see. Okay, so I can get an integer x such that x times t fall in this interval b and b plus 1. That means the integral part of x times t is b precisely, and now because of this bound we can see that x lies between 1 to b and b power n plus 1. Okay, x lies between. You have many choices possibly. I am choosing one. Okay. We have got hold of a x such that x times t integral part is b. Okay, so x times t is a t is already we know t by b power h1 minus 1. I am multiplying by x. Ultimately, I am going to multiply by x times alpha. So I am looking at the tail whether I have got my block or not. I am checking. Okay, x times t divided by b power h1 minus 1. The x times t you integral part and fractional part if you write. Integral part will tell you clearly the block and precise place. See, now you know why I have multiplied by b power h1 minus 1. You see in block B, if you see block B, b power n minus 1 is coming. Okay. So when I divide by b power h1 minus 1 throughout, I am dividing by throughout. Okay, so in the integral part. See, integral part of xt by b power h1 minus 1. Integral part of xt capturing b0 b power h n minus 1 divided by b power h1 minus 1. So therefore, I will get b power h1 minus n below. So it is in the right place. Actually, b0 I have pushed it. Okay. Similarly, up to bn minus 1. The fractional part already beyond digit 1 by b starts with 1 by b fractional part. I am multiplying by 1 by b power h1 minus 1. Therefore, fractional part will never give the anything this side. So carryover will not be there. So I am really through. Okay. So now I have to check whether x times alpha is going to be the same thing or not. No carryover should come from the front portion. X time fractional part of alpha, already we have checked alpha is like s plus t by b power h1 minus 1. Now I am multiplying by x. Then I plug value x times s I have to check whether carryover it is going to give or not. S is a rational number, X is an integer. X is a rational number, X is an integer. So this is anyway checking. On the next page I have calculated. Okay, yeah. So the denominator of XS, you see, X is a rational number. The rational number is maximum denominator is how much you know? You see that by definition, yes. Yeah, by definition the denominator is b power h naught minus 1. Okay, b power, and I am multiplying by integer. It is not going to change the denominator. Okay, it will go down if at all. Okay, therefore I will not give any carryover to my b naught. That should not be affected. Okay, so everything is checked. Now we have to check really x times fractional part of alpha and x alpha fractional part, both are same or not. That we have to check. That by looking at the difference, that is integer, therefore these two fractional parts one and the same. Okay, so this way, from you start with 0, the same position you can push it with some. The trouble with suppose if I assume some frequency nu for 0 block, then there may be a possibility I may, when I multiply by x, one place I will get this, but another x also, many x possibilities there. You see, I have not taken two blocks at the same time. I have done this for one particular x, both places it is happening. I have taken only one block and I have checked. So when I check, so I throw this and then I check one more. First 0, 0 block, I have cut it as a rational number, and next 0, 0 block I go. Okay, then I might end up in getting some other x, but this x is running through 1 to b power n plus 1, only finitely many, but I have infinitely many, these blocks are there. Therefore one will be capturing my thing. Okay, therefore the frequency will go down. That is intuitively, but one can give a proof. I will not get into. This is the final theorem. Suppose some block, suppose 0 block is appearing with a frequency nu, then given block will appear after multiplying by x nu by b power m plus 1, the block of length m. Okay, this is the idea I have told, but one has to give a kind of correct proof. I mean, in the frequency level. Yes. Yeah. Occurs infinitely often. Yeah, frequency either more or less. That's then it will not be normal. You want an example? Okay, so example as such. Okay, so I've forgotten the paper. So abundant of absolutely non-normal number, kind of American Math Monthly paper. He was constructing. I don't remember the example. Not exactly. It can be less, it can be very, very much. For instance, a rational number, one particular block will be appearing much more than other blocks. Other blocks will be 0. That is coming from, you see, irrational number. You see, all this Mahler's theorem meant for nothing to do with algebraic. Mahler's theorem is alpha is irrational. Any block will be appearing infinitely often. Infinitely often may be irrationality, there is no problem. But frequency will not be matching. That's all. Frequency computation, sometime it will be more, some blocks, sometime it will be less. Otherwise, infinitely often will come from Mahler's theorem. But x times alpha. I cannot say all irrational number, but x times alpha. by multiplying. Ah, no, that is. Ah. No, I guess infinitely often should be there. Only the frequency somewhere is going wrong. But frequency, except this conditional frequency, nobody can compute. You can cook up. So by Borel's conjecture in Cantor set, either you have rational or transcendental. Because algebraic irrational, if it is there, one digit is missing. Therefore, it cannot be there by Borel's conjecture. Only the endpoints. Borel's conjecture in Cantor set, ternary Cantor set, the endpoints rational numbers or all others are transcendental. By Borel's conjecture, implication. Yes, sir. No, it's Borel conjecture implication. Yeah. Yeah. Nobody knows. Nobody knows. If conjecture is true, then this statement is true. Yes, sir. Non-normal irrational should be transcendental, yes. Otherwise, again, except if you make sure that it is not rational. That's the problem. So, if you know irrational, of course, it is. Nothing will be there except rational or transcendental. But modulo Borel's conjecture. Yeah. Yeah, there is a possibility because no counterexample, no yeah. Not only this, but whatever generalized Cantor set also, because always we will be throwing one digit away. Therefore, it cannot be algebraic irrational. Again, countable measure, 0 set. Anyway. Cantor set. Maybe you should look at, no, Bujo does it. Let me try. In Cantor set, ternary Cantor set, he proved that you pick any, all irrational numbers achieves all kinds of irrational, what is that, measure of irrationality measure. Suppose given a real number, more than 2, okay, then there exists a element in the Cantor set whose irrationality measure is that. Suppose alpha is bigger than 2, then there exists a beta in the Cantor set whose irrationality measure is that alpha, which he has proved, 2008. So it means I cannot give you one. All type of numbers are there in Cantor set. So infinite, whether it is true or not, infinite means it is a Liouville number. That I don't know. I have to check the paper. 2008, this is Bujo. Bujo is the only guy, if at all, lot of results on digits. No, greater than or equal to 2. But almost, again, another theorem of Khinchin. Almost all real numbers in the sense of Lebesgue measure has irrational limiter 2. Okay. So E is irrationality measure 2. Pi we don't know yet. It is except again expectation is 2. It is at most 5 kind of. E it has been proved. Pi is always difficult.